This is an example of a slice-through three-dimensional model of something like you have a source like in the center of your Vedo zone, and what you see over there is that you see I can use this to. Yeah, here we go. So you have your source over here, you have your groundwater at the bottom moving from left to right, and you have a water table at the bottom. So what you see in this picture are gas phase concentrations, and you see like, so you have pretty large gradients from the source to the surface, and the gradients in concentration from the source to the groundwater are a lot less. So the loss typically the loss to the source to the surfaces are larger, as indicated by the gradients, than the losses or the transport or the transportation into the groundwater. What you also see in this picture is that the whole plume, the gas phase plume, is shifted somewhat towards the right. So that of course that's related to how the groundwater, how the contamination is partitioning to the groundwater. So, but you also, when you look at this picture, like maybe remember from the previous slide, you have like a low permeability zone in the center. So that effect of the low permeability zone is hardly visible when you look at these kind of systems. And I'll go into that a little bit later. So like Mike already he has indicated that, of course, we're dealing with many different types of sources. You can have like a relatively homogeneous system with multiple NAPL residual zones. We can have like a low permeability layer with a larger zone in there, or we can have like multiple smaller sources like clustered around, inside the Vedo zone. Now, when you look at these systems, right, what we know, we've worked with these systems a lot before, but we noticed that if you if you take a certain amount of mass and distribute that mass either homogeneously into a certain zone, or you say, well, let's distribute that more in a heterogeneous way. For instance, you spread the mass like evenly about that zone, or like say let's leave certain areas of that zone open, so you only occupy some part of the pore space with an apple. So when you do that, you can represent systems that you see in the right hand side. So and if you do that, you will see, if you then do simulations and you plot the well concentration in the groundwater as distance from the source center, you see that you see very limited differences between these kind of cases. And the reason for that is that as long as the vapor pressure or the concentrations in a certain zone are maintained over time, then you do not see differences. So you do not need to have like one block or rectangular zone or a very nicely defined geometry with a uniform NAPL concentration or saturations. You can have that NAPL being distributed in many different ways, as long as the vapor pressure that comes out of that zone is consistent. And if you have that, then you have responses like this in your groundwater. If you look at, for instance, this particular plot that you see over here, again, where you have distance from the source center, and on the y-axis you have well concentrations in micrograms per liter. What you see over there, of course, when you move away from the source, is that you see increasing concentrations, but when you move further away, you hit a maximum, and then the concentration decreases with distance. And what happens there is, of course, you have typical effects like of dispersion and all the types of mixing, but you also you see the effect of partitioning between the vapor phase and the groundwater. When you get close to the source, right, the vapor is partitioning to the groundwater, or migrating to the groundwater. When you move farther away from the source, you get partitioning back from the groundwater into the vapor phase. What I showed in the previous slide is that, in the discussion that Mike followed up on, is that as long as these vapor pressure are relatively constant over a certain zone, you can use that as the basis for that particular system. So we also looked at the effects of low permeability zones. And this picture over here, this conceptual model over there, appears that it is homogeneous. So we did simulation where we actually looked at many different layered systems with low permeability zones. I'm not showing that in the interest of time. But what we noticed that as long as these low permeability zones have a reasonable amount of available gas phase, so that the vapors, the VOC vapors, can actually transport through diffusion to these zones, they're not really forming like barriers to vapor transport. So what you can do, although this is like a uniform system, the way it's depicted, it actually can represent a layered system for that matter. So we noticed that for that particular purpose, that you only need to know the average water content over that particular zone. Whether you have low permeability zones or not, it really doesn't matter, as long as they're not fully saturated. So that's an important thing to remember for this particular system. So you have to have a vapor phase pathway for these contaminants to move to the groundwater. If that occurs, then the depiction is valid for these particular systems.
So Marty, I just want to add one other thing. So part of the reason for that is that this tool is focused on sites where vapor phase transport is important. So if you have a site that's really wet and it's primarily leaching, there are other tools you can use that are going to answer your question. But at the sites or at drier sites where vapor phase is important, the problem with the other tools is they don't account for that three-dimensional vapor phase transport, and so you couldn't really use them in a defensible way. So but because it's drier, some of these things go away, like the effective layers. As long as you don't have an extremely wet layer, as long as there's pore space available, that diffusive transport pathway is still valid. So I thought I'd better say that because that's the context. If you're thinking about a really wet site, that might not make sense to you.
So when you can address these multiple sources or these multiple configurations or the effects of these low permeability zones on vapor phase transport under these conditions, then you can say, well, I mean, you can come up with a limited set of parameters, including site-specific site-specific dimensions, failure zones properties, and source characteristics, right? And then you come up with a simplified system like that. So what is behind all this? So we use a STOMP simulator, that is a subsurface transport over multiple phases. It's a multi-phase simulator, working with the gas phase, the aqueous phase, and non-aqueous phase liquids. We apply that to this particular system, and so in this table over here, sorry, this table at the bottom over here. There we go. I've put all the different parameters that the user can work with, and I showed you the simulated values in these particular simulations that we have done. And in bold are the simulations that we've conducted for the so-called base case, and the rest are variations thereof. So, for instance, the gravimetric moisture content, we did simulations ranging from 1 to 9% of water. And you can see for all these other variables, see the range in parameters. So, for instance, and then you see also some of the limitations that we have to work with, right? You cannot have an endless kind of range that you can use for your applications. So, for instance, we talked earlier about the recharge, right? We varied it from 0.4 to 7.5 centimeters per year, and the reason behind that is that when the recharge is larger than this particular number, then you get a large contribution of the aqueous phase transport. So, some of the other ones are, for instance, if you look at the relative source position, it ranges from 0.1 to 10. So, if you put the source too close to the surface, right, then you have issues with the very quick transport of the gas phase into the atmosphere. When you put the source too close to the groundwater, then you have nonlinearities appearing from that particular application. So we want to stay in a reasonable range, so to justify this particular configuration. It is important to realize that for this particular application, the SVE process is not simulated, right? So we're looking at scenarios, looking at conditions where, for instance, before you apply a SV or after you apply a SV, you have certain conditions in the field. So what's happening to the contaminant in your source zone? How is it being transported over time? So the actual SV process is not being simulated in this particular case, and that's the basis of your decisions. We're going to come up with systems that actually predict like conservative type of concentrations for your decision making. So we do not want for these steady state simulations, we do not want the sources to deplete over time. If you do that, then your system will not come to a steady state where you have a diminishing source strength. So sorption, of course, when you have vapors like the VOCs that we're dealing with at the different sites, most of these vapors, they petition into groundwater, but they also sorb to the solid phase. Now, however, when you look at long-term behavior of these sources, you can have, of course, adsorption, but it's not going to affect really the distribution over time. So, for instance, when you start out in a clean system and you put some non-aqueous phase liquid there, of course, the vapor phase distribution will initially be a function of time. So, So when you have strongly sorbing contaminant, then that vapor phase will spread slower than a contaminant would be that is not sorbing as strongly. But over time, the distribution will be the same as long as you have provided enough mass for that to occur. So, for instance, I showed two pictures, one with a system simulation after about 10 years of a vapor phase zone, vapor phase source emanating vapors into the subsurface. Now, you see on the left-hand side and right-hand side, the left-hand side has a contaminant that's not non-sorbing, and the right-hand side you have a contaminant that is moderately sorbing, and when you compare these two figures, there are no differences over time. So sorption over time is, so when you go to steady state or an equilibrium kind of distribution, is not a factor anymore. So when you vary these parameters, you see some of the parameters have like a linear effect on concentration, some have a near linear effect, and some have a highly nonlinear effect. These are some examples of parameters that have like a linear effect. The source on the left-hand side, you see the source gas concentration, right? If you increase that, you see that well concentration respond in a linear fashion. That makes sense, right? That's what you want to happen. It's a good test of your model for that to happen. So if your concentration goes up by a certain factor, then you want to have linear response in your concentrations. So on the right-hand side, I plotted 1 over the Henry's coefficient, and you see linear effect of that too. And these are the kind of relations that we actually use, right, to correlate, to go from carbon tetrachloride to other components into our system. So when you go to other parameters, you see like you see either near linear or nonlinear effects. So this is an example of the source area. So if you increase the source area, so you see that the well concentration increases, but not in a nonlinear way, and also certainly not proportionally. So in the top left-hand corner over, you see that's for the simulations are shown for a lower groundwater velocity, and the right-hand side for a higher groundwater velocity. And what you see there is that for the lower groundwater velocity, the concentrations, the well concentrations are larger than for the simulations that are run with higher groundwater concentrations. And the reason that is when you use lower groundwater concentration, the contaminants that actually move into the groundwater have a larger time to mix with the groundwater, leading to higher concentrations. So all these results are logical, but also what you see is that for the lower groundwater velocity, that the concentrations have a larger range. You see that the spread in the vertical spread in well concentrations for the lower velocities are larger than in the right-hand side than for the higher water velocities. And that of course had to do with the mixing time that you allow the contaminants to work with the groundwater. So when you have a faster flow, the contaminants move into the aqueous phase, and the aqueous phase when the flow is faster, so the mixing time is less. Therefore, the spread between these, the differences between these concentrations are less too. So this is an example of a highly nonlinear parameter. That's relative source position. That is, if you look at your left-hand side, that's L1 over L2. So when that number is small, that means that your source is very close to the surface. When the number is high, the source is close to the water table. So when your source is close to the surface, your concentrations, of course, in the groundwater are a lot smaller than they are when the source is closer to the water table. Again, you see the much larger spread for the lower velocities than for the higher velocities.